Hello students, let's start with the next topic about syllabus, that is nothing but a viscosity. Now might be all of you will learn about viscosity. Some fluids are viscous and some fluids are more viscous and some of them are less viscous. So what exactly viscosity is? For that, according to the book, let's start with one of the best example as they have given in the book. When we just taken a glass in which the water we have taken, when we try to drop a water from the glass, it is easily fall down from the glass because its viscosity is less. Apart from this, if we take in the same glass same amount of another glass, we have taken blank glass in which we have drawn some honey or some syrup, some medicinal syrup we have taken, or suppose some honey we have taken, and we want to drop that honey from that glass. It is seen that it will take longer time to fall down. Why it's so? Because its viscosity is high, it is more viscous than the water. So this is a basic difference, and this property is very important when we see the proper motion, fluids in motion. This property must be understood very well. So might be you get little bit idea about viscosity. If you compare the water with honey, water is less viscous than the honey, and that's why water can easily flow as compared. Honey will take a lot of time to flow as compared to water, so its viscosity is more than that of water. So that part we have just seen with example. Now here one more thing to remember is that if you see in your book, there are two diagrams they have given to explain this. The first diagram they have shown as like this. If the fluid is moving like this, such type, when we flow the fluid, if the fluid is moving like this, that means what? In this case, if we observe, all the layers are not moving with the same velocity. The central layer is moving with more velocity, then the remaining part comes with a less velocity like this. This is a flow of liquid which is more viscous, and that is, we can say, viscous fluid. The fluid whose viscosity is more viscous fluid flow like this. Their different layer has a different velocity. Apart from this, the fluid just like a water we have seen. This is for honey, we can say. So this is when we just try to flow the honey, it will flow like this. Different layer move with the different velocities. But in case of water, if we say, in case of water it is less viscous, so all the layers will move with the same velocity. So this is the diagram we can draw for flow of water. In this case, all the tips come in exactly, they are parallel. Here also they are parallel, but their velocities are same. Their flow at the same time, whole fluid is flowing, and that is nothing but because it has less viscous. Now this viscous part got by this honey as compared to water. Honey is more viscous. Now in this case, why these forces get created? These forces get created due to friction. Due to friction. Friction may be the internal friction between the molecule as well as external friction between the molecule, or we can say fluid, and the surrounding. Depending on that friction, this property comes into existence, that is said to be viscosity. Now here we have to learn about how this property of viscosity just affect the flow of fluids in the pipe, like maybe gas or maybe fluids they are moving in the pipe, how it will affect that flow, that we have to consider. So in your book they have taken an example of river, flow of river water. Might be all of you are well known about river. Some of you might be went to the river, inside the river you can observe, or you can whenever you go in future also, if you don't, suppose this is a two banks, this is the bank of the river, so this is one bank of the river, this is another bank of the river. This bank of the river are nothing but a fix, they are not moving. Okay, within this part the river is moving, so water is flowing like this. Within this part different layers of waters are flowing. Now in this case it is seen that when we observe that the layer which is close to the bank, like this layer close to the bank, and here the same layer comes here, the layer close to the bank, the velocity of this layer is very less, or we can say velocity is small. And as we go from any one of the bank, if you go toward the river, it is seen that here the velocity is less, again increases, come to this much, again increases, and finally at the center velocity is maximum. So this is velocity at the center. Again beyond the center, if you try to go to that side of bank, it is seen again the velocity decreases, decreases, and finally very less velocity near to the bank. From this we can say the different layer of the river, they are not moving with the same velocity. Now why they are not moving with the same velocity? Because these two banks are here, to these two banks oppose some drag, they exert some drag force on the flow of liquid. That's why the liquid in the river or water in the river near to the bank has a less velocity because of that drag force exerted by these constant layers, constant and fixed layers. And that's why at the center the flow of water is much more in the river. So this is the example they try to explain this. Now they have given on next page the definition of viscosity. Viscosity is a property by virtue of which, this is a definition you have to prepare, by virtue of which the relative motion between the different layer of the liquid. Viscosity is a property of fluid by virtue of which relative motion between different layers of the fluid experience a dragging force. Relative layers experience a dragging force, and this dragging force is called as a viscous drag, or that is said to be due to the viscosity. Now here in liquid, the viscous drag forces are due to intermolecular cohesive forces, force of attraction between same molecule, that is responsible for viscous drag in liquid. But in case of gases, that viscous drag is nothing but what? Due to collision of air molecule with each other, gas molecule with each other, and their random motion, that will oppose the motion, and that will produce a viscosity in case of gases. Apart from this, in case of turbulent flow or in laminar flow, we can say first. So in case of laminar flow, it is directly proportional to relative velocity of the layer. But in case of turbulent flow, it's not so. It is directly proportional to some higher powers of the relative velocity. So that is nothing but this part they have mentioned. Below that they have given the equation, that is velocity gradient. What is the velocity gradient? And simple thing, as distance get changed, how the velocity get changed, that can be measured, and that is said to be velocity gradient. So it is velocity gradient we can represent like this. Velocity gradient equal to change in velocity with the distance. It is change in velocity, suppose dv, and change in distance is dx. So change in velocity with distance is said to be velocity gradient. Okay, so this is velocity gradient. After that we have to see the coefficient of viscosity. Now what is the coefficient of viscosity, that we'll see. So coefficient of viscosity, in this case Newton's laws of viscosity says that the force, viscous force, is found to be directly proportional. According to Newton's law of viscosity, the viscous force is found to be directly proportional to area of the layer. Suppose F is a viscous force, it is found to be directly proportional to area of the layer, okay, and it is directly proportional to velocity gradient dv by dx. So this is nothing but one of the formula that is given by Newton's law of viscosity says that the viscous force is directly proportional to area of the layer as well as directly proportional to velocity gradient, change in velocity with distance. And according to, if we just remove this proportionality sign, say we take some constant here, and that constant is suppose this sign, and this is said to be eta, then eta is said to be coefficient of viscosity. So here F equal to n into a, sorry, eta into a into dv by dx. Eta is said to be coefficient of viscosity. From this you can find out the value of eta, coefficient of viscosity, F divided by a into velocity gradient dv by dx. From this we can explain coefficient of viscosity can be represented as the viscous force per unit area per unit potential gradient, per unit velocity gradient. So coefficient of viscosity can be explained as the viscous force per unit area per unit velocity gradient, that is said to be coefficient of viscosity. And its unit, if you just put the values of all unit here, we can say its unit is Newton second per meter square. And here this is a SI system unit. In CGS system, same viscosity or coefficient of viscosity can be represented in another unit, is said to be poise. It is said to be poise. If you remember, in 11th standard, in the 4th chapter, we have just find out conversion factor 1 Newton equal to 10 raised to power 5 dynes. Such type of equation we have derived. So this is dyne is nothing but what? CGS unit, and this is MKS unit or SI unit. This conversion we have find out. So in your book here, they have given the option, use your brain power. So here we have the two units. This is SI system, this is CGS system. So what is the brain power you have to use? You have to find out conversion between this. 1 Newton second per meter square equal to how many poise? That you have to find out by using this application that we have learned in 11th standard. Try to find it out. After that, in that the next yellow color portion is there. There they have mentioned microscopic view of viscosity. Just I will review this. What is microscopic view of viscosity? Here what they have done in the picture, they have taken two layers, X at the bottom and Y at the top. In between these two layers, there are three intermediate layers they have taken. This is X, this is Y, here C, B, A. Three layers they have taken. And it is seen that this A layer is, X layer is fixed, Y layer is moving here with velocity V. So Y layer is moving here with velocity V, and this is a fix. And due to that, this fixed layer exert a drag force on the layer Y. And how it will affect, how there is change in momentum, transfer of momentum from layer A, B, C, from Y to C, C to B, B to A, and finally to X. How the momentum of particle get transferred and how it will exert a drag force. They try to explain the same thing in this topic. Just try to revise it, just try to read it once only. Now let's go to next topic. Remember this topic is there. In this remember this topic, what they have just mentioned, they have mentioned that coefficient of viscosity of liquid is found to be, just they have mentioned coefficient of viscosity changes with a temperature. In case of liquid, coefficient of viscosity decreases with the temperature. As temperature increases, eta decreases for liquid. But for gases, exactly opposite get occur. As temperature increases, coefficient of viscosity also get increased. So that part they have just explained by using the table they have given below. The different fluids, air, water, machine oil, they have given different temperature they have taken, and coefficient of viscosity they have given here. Then the next topic of our syllabus is what? Stokes law. There is one scientist whose name is Stokes. Stokes has given one law which will give the relation between when we drop a sphere, exact solid sphere, in some viscous medium, how the force it will exert some force, how the drag force it will experience, that was given by this, and that is said to be Stokes law. So let's start with this Stokes law. So this Stokes law is nothing but what? When any sphere, spherical shape molecular sphere get fall in a viscous medium, viscous liquid, suppose we have dropped the sphere, how it experiences a force, that we have to see. So what this law states, that viscous force acting on a sphere, viscous force acting on a sphere falling through a viscous medium is found to be directly proportional to radius of the sphere, directly proportional to velocity of the sphere, and directly proportional to coefficient of viscosity. If we consider here viscous force was represented by, if we represent viscous force by F, then this viscous force experienced by F we will take viscous force experienced by the sphere when we fall it into the medium having some viscosity. It is found to be that viscous force is directly proportional to radius of the sphere itself into velocity of the sphere itself into what? The coefficient of friction of that liquid. So that is nothing but we can write F is directly proportional to R is a radius of the sphere, V is a velocity, eta is a coefficient. If we remove the proportionality sign, if we take constant of proportionality, that constant of proportionality comes to be 6 pi into eta into R into V. So this is nothing but an equation, mathematical form of Stokes law, which says that already we have seen the statement, not now we are not going to see again. So this frictional force, or we can say when we drop that sphere, heavy sphere in some medium viscous liquid, it is seen that it will experience some force, viscous force, and that viscous force experienced by that sphere is directly proportional to radius of its sphere, directly proportional to velocity of the sphere, directly proportional to viscosity of that medium. Now here, this part just given in your book, equation 2.36, you have to remember this equation, viscous force experienced by the sphere when we drop it into the fluid which has some velocity. Now let's go to next topic, that is nothing but what? Terminal velocity. So let's start with this terminal velocity. So it is terminal velocity. So terminal velocity means what? To understand this terminal velocity in detail, first of all, let us consider spherical object. Now let's consider same spherical object. When we drop that spherical object to the viscous liquid, how the forces, how many forces it will experience, that we have to see. Suppose this is small tube we have, suppose some longer tube we have taken, and through this longer tube we have filled this tube with some liquid, like this some liquid we have filled in the tube which has some viscosity. Viscous fluid we have kept in this liquid, and we are dropping here one sphere. So this sphere is dropping inside the liquid. Okay, when this sphere goes downward in the liquid, it is seen that it will experience some forces. What are the forces experienced by this sphere when we move into the viscous fluid? That we have to see. The first force is a viscous force which is moving in upward direction. First force is a viscous force which is moving in upward direction. Second force experienced is nothing but what? Force due to gravity. That is nothing but a Fg moving in downward direction. This Fg moving in downward direction due to gravity of Earth. Some force is moving in downward direction. This is a viscous force. According to Stokes law, it moves in upward direction. Apart from this, some liquid is below this, and this liquid exert an upthrust force, that is said to be beyond force, and that beyond force or upthrust force was represented by Fu. Again, that Fu moves in upward direction. So these are the three forces acting on this sphere when we put that sphere in that viscous liquid that is falling downward. One downward force is nothing but a Fg, that is Fg equal to what? Fg is nothing but a force due to gravity, and that we know this force due to gravity is mass of the sphere into acceleration due to gravity, mg. And this upward thrust and this beyond force, upward thrust and viscous force moves in opposite direction. Now here the resultant force we can write here, resultant force F equal to this force due to gravity minus downward force minus upward force minus Fu plus Fv. So this force we get here, resultant force, change in the upward and downward force we can find out. At certain equilibrium, when this resultant force is 0, we can say that Fg equal to Fu of thrust plus force due to the viscous force. That means at this will occur at equilibrium. When resultant force will be 0, we can say Fg equal to this. So we can write this equation here. Now that we have to put here, before going into detail, let us consider this is a sphere whose mass is m, whose radius is small r, mass is m, radius is small r, and its density is suppose rho. And here the liquid has a density suppose sigma, and this liquid has a density sigma and coefficient of friction as a eta. Let's assume these factors. So sphere having a mass m, density rho, and here r is the radius of the sphere which is going through this liquid, and this liquid which has a density sigma, coefficient of viscosity as a eta. Now let's go further. Now derivation. Now total upward force, this is a total upward force must be equal to total downward force. So this Fg is downward, Fu plus F is upward, so that we have equate the equation. Now we have to put the values. So Fg equal to what? Mg, mass into acceleration due to gravity. Fu is what? Beyond force actually. Before going to Fu, just write down Fe first. It is nothing but what? Viscous force. According to Stokes formula, what is the value of this force? I will write this same like this, Fv plus Fu. Doesn't matter. You are adding both the forces. So take Fe first according to Stokes law. What is that? 6 pi r v rho. Just before we have seen 6 pi r v, it's not rho, it is eta, r v into eta. 6 pi is a constant, so r v into eta. This is nothing but a viscous force according to Stokes law. We have just written this formula according to Stokes law. Now let's go further. We want to determine what is this upthrust force. Upthrust force is nothing but what? Here it was given by 4 by 3 plus 4 by 3 pi r cube, 4 by 3 pi r cube sigma into g. 4 by 3 pi r cube sigma into g. What exactly this force is? This is nothing but this force is nothing but m into g in upward direction. Upthrust, exactly opposite to weight acting in downward direction. So this is upward thrust. So here how it becomes mg? This part up till now, this part, what is this? This is a mass. How it is find out? So see, so density equal to mass per unit volume. Density of the fluid is here, so it is sigma, mass divided by volume. What is the mass? Volume into density. What is volume of sphere? It is sphere falling, na? So it is 4 by 3 pi r cube into sigma. This is the value of mass, and if we multiply it by g, we get this mg. We get this equation for upthrust. Same thing. Same thing here, m is there. We have to put here the value of m, but here it should not be sigma, it should be rho, because this is for sphere. So we can write this equation as 4 by 3 pi r cube rho into g equal to, I hope you got this. This thing already we have done a lot of times. So let's go directly. So 4 by 3 pi r cube rho into g, that is equal to what? 6 pi eta rv plus 4 by 3 pi r cube sigma into g. Is that clear? Now move this term to this side and move this term to that side. So what we get? 6 pi eta rv equal to 4 by 3 pi r cube. Okay, this 4 by 3 pi r cube, 4 by 3 pi r cube. Common is there, g is also common. G is common. Outside the bracket, what is? Sigma minus rho. Sigma minus rho. Or we can take a, just if we shift this term to this side, what we get? Rho minus sigma. So it is rho minus sigma. Just don't move this term. Move this term to this side. Keep it as it is. Move this term to this side. So we get 4 by 3 pi r cube rho g. G is common. This term is common. Rho is different. Sigma is rho minus sigma, that we get here. Now further, just you can solve this also. Further, just I want to solve this for what, which value we want to find out. Here we are interested to find out terminal velocity. So v, terminal velocity we want to find out. So find out v equal to 4 by 3 pi r cube into g into rho minus sigma divide by this term goes to that side, 6 pi eta into r. So this pi get cancelled with this pi, this r get cancelled with cube, it becomes square here. Okay, 6 comes to be here, 6 3s are 18, so it comes to be 2 by 9. So finally what we get, it is 2 by 9. Okay, r square g by 6 eta into rho minus sigma, and that is v equal to, and this velocity is said to be terminal velocity. Just make it confirm. So 2 by 9 r square g by 6 can't go now, already 6 into 3 18, 6 into 18 we have done, so 6 can't come here. Directly eta, r square g divided by eta rho minus sigma. This is nothing but a terminal velocity of the object. And before this they have just mentioned, when equilibrium gets occur, at that time the velocity with which the sphere goes in downward direction, that remains constant, and that velocity which is constant is said to be terminal velocity, given by this equation. Same thing here, eta is there, you can find the value of eta also. Take eta here, move this v here, so we can find out coefficient of viscosity also. So in this fashion we have completed the chapter. In next period we will start a new chapter, that is nothing but a kinetic theory of gases and radiation. Might be you are confused about some topics are remaining in this, but see what topics are remaining. Equation of continuity, that was keep this year. After that, Bernoulli equation and its application of Bernoulli equation, that are also reduced this year in the syllabus. So no need to see that topic. For your understanding and for JEE NEET syllabus, try to review it. Just read it once and leave it. But just read it once for your sake of understanding. But in board examination, no question will be asked on this topic. So in this fashion, we will stop here. So watch my video, then read the same topic, and tomorrow, in next video, we will start with the next chapter, kinetic theory of gases and radiation. Okay, thank you.